Okay, well, it's very exciting to be here at this conference. I want to really thank the organizers for putting together such a great day, and I think I've learned something new in every single talk, which actually says something since we're all going around giving a lot of talks at the same conferences, but everybody's working so fast that there's new papers every time. And actually, I thought it was really interesting, the last two talks, Victor's talk and Larry's talk this morning also picked up this theme of sample splitting, which is also going to be a big theme in my talk. And I think it's interesting that I think we all have had our own journeys to, like, from hating or feeling kind of embarrassed to talk about sample splitting because it sort of feels like you're cheating and it seems so much more satisfying to prove long, complicated theorems. But I do want to emphasize that at least at the end of my journey is like, it's sort of like, how could you beat it? You know, you could prove some very complicated theorem, but how are you going to get rid of a factor of 2 in your theorem when you are using the data to choose your model? And so I guess partly I want to make sure that our hesitancy as sort of theorists that sort of feel embarrassed about taking such a cheap out doesn't keep us from actually advocating to empirical people to do it, because in an actual real data set where n isn't at infinity yet, the sample splitting I think is just going to work so much better. So as we go out and sort of advocate to economics to use all these cool tools, we're probably going to systematically get the wrong answer unless people don't sample split. So we should just maybe all collectively get comfortable with it now and save the profession a lot of wrong answers. And so I actually thought it was awesome that Victor was also showing that today. If somebody as technically astute as Victor thinks sample splitting is okay, then maybe the rest of us can too. And really, Victor's talk is, he's been such an inspiration to me in all of this work. And I think one of the things that's really interesting out of his work that I try to always talk about very early in any kind of talk I give about machine learning and econometrics is just that this idea that prediction, it's not just that it's not the same objective as causal inference, but it actually really can lead you astray. And so they have this lovely Journal of Economic Perspectives paper that kind of boils that idea down without all of the math, but you can just really see it. And so I basically recommend that article to everyone, any machine learner particularly, who just can't understand why we would ever want to do anything other than mean squared error of our predictions. Victor's paper is a great place to start on that as well, his sort of easy throwaway JEP paper, but I think it can really be influential for the audience. So today, I'm really going to pick up sort of where Victor left off in terms of like thinking about the ways that machine learning come into econometrics and the part of causal inference. So although Victor's stuff covered a wide range, a lot of it was talking about estimating a low-dimensional parameter, like an average treatment effect, a local average treatment effect, and so on. The other big sort of success of machine learning, and I guess, I'm sorry, and so in a lot of economic environments, to make that kind of inference plausible, we want to control for a lot of covariates. And so we have lots of environments where if we had lots and lots of confounders, if we could control for them flexibly, we would be able to do causal inference, and those methods really help us take off in that direction. But another thing that machine learning has been very good at has been sort of doing personalized recommendations, and that's sort of one of the things that it's used for very much in practice. It's actually kind of funny, just parenthetically, that like recommendations are considered a prediction problem, when in fact, like any kind of objective that you would want to use recommendations for is actually a causal problem. But I'll just put that aside. Okay, so heterogeneous parameter estimation. So generally, like heterogeneous treatment effects are at the heart of many modern statistical problems, personalized medicine, targeted advertising, recommendations, and issues like fairness in machine learning, whether machine learning is going to make us discriminatory in some way. And of course, heterogeneous treatment effect estimation is closely related to the problem of optimal policy estimation. That is, like, what ad should I show someone? That's a policy problem. What's the best policy for assigning individuals to medicine, to ads, and so on? Can I reject the hypothesis that my new assignment policy is better than the alternatives? Might want to do things like that around evaluation. So I'm not going to talk so much about this piece today, but I'm also working on that in related work. And I think this is actually an area from machine learning that needs to get brought more into economics. There's a subfield of machine learning that's contextual bandits, which basically does take a causal framework, has brought in ideas like propensity score weighting and so on, optimal experimentation. If we want to think about, what do we need to do if we want to bring in machine learning for treatment effect heterogeneity, there's a few things that slow us down. First of all, we know machine learning methods perform well in practice, but many don't have well-established statistical properties, although back even in the 90s, there were some economists trying to prove properties of neural nets and so on. And so why are the statistical properties so important? Well, economists, of course we need to publish our papers, duh, so of course we need confidence intervals. But if you go away from just the conventions of our field, why is it that we're so focused on statistical properties rather than just holding out a test set? And the answer is, of course, that we don't know the ground truth. Why are people arguing like crazy about the local average treatment effect or the average treatment effect, or whether the local average treatment effect is the marginal treatment effect and so on? Why are people arguing so much about these things? Well, part of it is that we don't know what the answer is. If I had a held out set, I still wouldn't know what the causal effect was in my held out set. So in a prediction problem, if you hold out 10% of the sample, you can see how well your model does by how well you predict the outcomes in that held out set. So that's all you need. And I could have lots of theorems about n going to infinity, but why the hell do those matter? Because I can just look in a test set and see in my real data set with its real properties how my model does. So theory is kind of useless. Maybe it gives you some guidance, but you can trump the theory with the actual data. In contrast, if you're estimating a causal effect, you cannot trump the theory with the actual data because you don't know the truth. So we must have theory. It's not like optional. It's not just a convention. It's not just something that we all like to do because we have to publish our papers. It's actually kind of fundamental. But of course, we do need them to publish our papers, and we do need them to get drug trials in. And actually, even in tech firms, where you might say, oh, people don't care, they do all these predictions, all these machine learners. Actually, if any machine learner wants to get a bonus in that tech company, they actually test their algorithms in an A/B testing platform, and the standard errors are crucial. And if your algorithm isn't statistically better than the incumbent, it doesn't get shipped. You don't get your bonus. So actually, these things are important, very important in practice. And so we're going to be interested in trying to do that with heterogeneous populations. Now, I want to highlight that actually there's many different possible questions of interest about heterogeneous treatment effects. So I've seen people stand up and say, oh, well, of course we're interested in X, and of course we're interested in Y. And actually, I just want to say, I've thought about this a fair bit. That's I think, is a bad way to think about it. There are different questions and different methods for those different questions, and all those questions are valid. So it just depends on what you want to do. So I have a paper that just came out in PNAS about identifying subgroups, and I'll show you a little bit more about that later. But basically, we use regression trees, and we find subpopulations. We choose them on the basis of treatment effect heterogeneity. And so we'll say, OK, men above 60 and that have these pre-existing conditions have a high treatment effect. So machine learning people will say, well, why would you want a subgroup? That's obviously not as good at predicting as something that gave personalized predictions. And say, well, for some context, I do want a subgroup. Like if I'm going to put a poster on a wall and doctors have to memorize it, if police people have to memorize it when they go out on the street and decide who to stop and frisk, if your computer has to have a lookup table, it might be easier for it to look up which cell you're in than to compute the result of an algorithm. So there are many, many applications, and you see it in the business world as well, where you actually choose to use subgroups. Now, what's going to be beautiful about the subgroup analysis is that I'm going to be able to give you sort of perfect standard errors using standard sample splitting, standard errors that can have 1 million covariates and 1,000 observations, and I'm still going to give you perfect coverage. So that's going to be really awesome, that I'll be able to give you perfect answers. And the way I'm giving you sort of good coverage and confidence intervals, even if I have many, many covariates and a non-sparse model, is that I've actually changed the question on you. I'm going to make subgroups, and then I'm going to give you treatment effects in the subgroups. And so I can make sure my subgroups are big enough that the law of large numbers kicks in on the subgroup. And so I can tell you an estimate for the subgroup. That is a different problem than giving Larry a personalized estimate for you. If I try to do a personalized estimate for Larry, then my problem gets very complicated, I'm going to have trouble with coverage of confidence intervals, because it's going to be very hard to find enough people like Larry to have exactly. He's already told us he's an outlier, and I'd like to be more like you, Larry, and then we can get good confidence intervals. But I've got a ways to go until I can get into your neighborhood. Other types of questions people have asked, and I think are also very valid and interesting questions, trying to just test for heterogeneity across all covariates. So if you're a social scientist or another kind of scientist, you might just say, I want to know about all kinds of treatment effect heterogeneity, not just one partition of a space into subgroups, but I want to test everyone. And so John List and Azim Sheikh and Zhu here at Chicago have a paper about doing multiple testing correction in that type of environment. You could also ask questions about robustness to model specification. That's something I've explored, or do personalized estimates. So I'm going to focus most of my time today on personalized estimates. But there are lots of other things that you could do, and I just want to say it's not that I think one is better than the other. Of course, so far, and I think in Victor's very first papers and in my first papers as well, the sort of the natural place to start from going from prediction to causal inference is to focus on simple examples where there's just one treatment variable, like a single parameter you're interested in, a treatment effect, and you have a fairly simple model. What we saw in Victor's work, and also the direction that I'm going to take today, is now, once we kind of figured out the math and really got things going on these simple problems, we're now kind of going to 2.0 and trying to take these methods to more complicated models of the types we're used to doing in economics, whether they're panel data models or other types of models. And so that's going to be the new work that I'm reporting on today. I'll mention, just as we already saw today, but the Chernozikov group has done really amazing work, mostly focusing on low-dimensional parameters. And I've also recently been working in the area of average treatment effect estimation as well. There's also been a number of papers just in the last couple of years on heterogeneous treatment effects, some of them using lasso, some of them using targeted ML. And I'm going to be today talking about random forests as a class of models for this, but different methods might work better depending on the data structure. So what we're going to propose in the new work, the newest work I report on today, are going to be random forests for semi-parametric parameter heterogeneity. So, historically, we did things like semi-parametric generalized method of moments or semi-parametric maximum likelihood to try to get sort of more heterogeneous effects out of a model. So you might do local linear regression. That's probably the most commonly used in economics, where basically you run a regression, but you weight observations close to your observation of interest. And the big problem with that, it's like there's no conceptual problem with it, but just in practice, if you have more than 2 or 3 or 4 covariates, it starts to do badly. And so what we're going to want to do today is bring in random forest methods to try to kind of diminish that curse of dimensionality and make these kinds of local methods work better. And so the forest methods are going to be able to determine what dimensions are important for being nearby and reduce the curse of dimensionality. And particularly, it's going to be particularly helpful if you have covariates that don't have any effect at all. And the random forest is going to do a really good job of ignoring those covariates and only focusing on the dimensions that are important. And so some of the things we're going to try to propose are that we're going to deal with another concern as well. I've actually been working on this for a while, and a lot of my initial attacks on generalizing models, random forest models, had the idea that you were going to build a tree, and then inside each leaf of the tree, you're going to estimate a model, and then you would somehow average up the results. But that actually breaks when you have complicated models, because a lot of these models won't really estimate very well when you have a small number of units. So instead, what I'm going to do is I'm going to use the random forest methods to come up with weights, but then I'm going to estimate the model like using more like local linear regression, where in principle all observations can contribute to the estimation at every point. They're just going to be weighted differently. And so we're going to also talk about how to get splitting rules in this environment that are customized for the objective, and we have a computational trick. Okay, so that's where I'm going. What's work that's related to this? Well, this is a very old idea, as I said, going back decades. There's been applied in statistics and econometrics. We're also going to be related to a literature on score-based test statistics for like structural breaks and so on. We're going to use that to help figure out where heterogeneity is. So just very quickly, I think everybody in the room is familiar with the potential outcomes framework. So that's what we're going to use for the basic causal effect examples. So we have X's are going to be our covariates, Y's are our outcomes, and W's are our treatments. And again, the reason prediction is different than causal inference, and this framework can be stated very simply. We don't actually observe both potential outcomes for any person, so there's a missing data problem, and that's why we don't have the ground truth. We don't know, in a holdout sample, we don't know Costas's treatment effect. and so we can't know if we predicted it well or not. And so the goals we're going to be thinking about in the simplest case would be to estimate a conditional average treatment effect, so the expectation of the treatment effect conditional on x. And similar to Larry's talk this morning, he was talking about mu of x, so that's just the conditional mean. In some sense, this is just the difference of conditional means, which is why it was a very natural first step to take away from prediction. Under unconfoundedness, we have a hope of being able to measure that, the quantities identified, if the treatment is independent of the potential outcomes conditional on enough x's. And so one reason, again, machine learning is going to be very helpful is that if we condition on all these x's, then lots of x's, the unconfoundedness will be more plausible. So what's a baseline method to compare to? Well, I'm going to use KNN as a comparison because it's one of the things that's most similar to a tree in a forest. Now, machine learners often say, like, why would you use KNN as a benchmark? Nobody uses something as stupid as nearest neighbor matching. You know, like that's a ridiculous method. Like you would use, why wouldn't you use some neural net or something else as a baseline? But what we want to do is focus on methods that have statistical properties established. And so the KNN method, also kernel, basically is the same as KNN from a statistical perspective, roughly. So this is a good method. Basically, if I want to get somebody's treatment effect, I take Larry, I find people like Larry who were treated, and I find people like Larry who were controlled. I take the difference of their means, and that's going to be the estimated treatment effect for Larry. But it's going to have an acute curse of dimensionality, because if I think of all of Larry's dimensions, it's very hard to find anybody who's anything like Larry, and so my estimate of Larry's treatment effect will be biased towards the mean. So adaptive nearest neighbor matching is basically going to be like nearest neighbor matching, except I'm only going to match on dimensions that are important. And I'm going to focus on matching on things that are important, and I'm going to look at the data to tell me what dimensions are important for matching. It's got a great empirical track record, and people have also brought it specifically to the treatment effect setting, but without any theoretical foundation in the Bayesian context, without any guess of whether you're going to actually converge to the truth in the classical setting without any kind of asymptotic normality results. And it turns out that the out-of-the-shelf R package for random forest does not have any of the desirable properties you would like. It's not consistent. It's not asymptotically normal. It fails these. It's not just that we don't know. We know that it doesn't work for statistical properties. So when I started looking at this, I was like, okay, this method is used 50 gazillion times. Surely somebody's graduate student somewhere wondered whether the random forest was consistent and asymptotically normal, and it's just a matter of finding the papers. So I downloaded like 300 papers, and I tried to read them all on airplanes, and it turned out that nobody knew the answer. It turned out that you could make random forests consistent by changing them a little bit, and one way you could make random forests consistent is by using sample splitting. Another way you can do it is by having very big leaves. So the idea is that, well, I've got this algorithm where I'm going to peek at the data to decide what variables are important. So of course I'm going to overfit outliers. Of course I'm going to do overfitting. And you can come up with examples where you're going to go wildly wrong. So how could I fix that? One is that I just have very big leaves, and so that averages out. And the other is that I use one data set to build a tree and another data set to estimate it, and I do that over and over again. Then I thought we had found actually a paper that did solve the problem, and that's a paper we talked about this morning, Mensch and Hooker, which now just came out, and I read the working paper. It looked like it talked about confidence intervals and it talked about asymptotic normality, but I was confused because it didn't actually do any of the things I knew already that you needed to do to make the random forest consistent. So it turns out that actually they're not consistent, so they prove that random forests, whatever it converges to is asymptotically normal because it's an average of a bunch of things, but it doesn't actually converge to the truth. And so you might think maybe they just need to fix their theorem, but actually the flavor of the forest they study does not converge. Like you can prove that it doesn't. It's bias dominated. The proof requires small sum samples, which limit the depth of trees and contribute to bias, and they also don't require sample splitting. So both of those reasons screw it up. Even if you did sample splitting, the proof method requires small subsamples, which actually preclude you from getting things to work. So it's part of the way there, but it doesn't actually, you can't actually use it. If you could, I would have and wouldn't have written the paper, but it didn't. So let me first talk about, so there's actually a pair of papers I'll briefly talk about. I wasn't going to talk about this one, but then Larry inspired me to. I want to talk first about the trees. So forests are averages of trees. I have a paper about the trees and a paper about the forests. So the paper about the trees, we introduced something called causal trees, which defines neighborhoods for matching based on recursive partitioning. We advocate sample splitting, and actually the first versions of the paper, we advocated sample splitting, but we didn't actually anticipate the sample splitting when we were building the trees. And then once I got over my hump and realized sample splitting was a feature and not a bug, it made the paper much more interesting because we went back and we figured out that the splitting rules that are normally used for regression trees are actually the wrong ones to use if you know you're going to sample split. So the normal regression tree splitting rule sort of thinks of whatever estimator you have is the final estimator. It's not a random variable. And so you're just testing whether it balances bias and variance. If I know what I'm going to do is use the data to choose a tree and then go and re-estimate that tree on an independent sample, I know I'm going to be unbiased. So I don't have to worry about bias. And I do have to worry about variance. So when you do some math, it turns out that the optimal way to build trees, if you're going to do sample splitting, is a little different. And it's very lovely because it actually is going to tell you not to make leaves too small because they'll have a lot of variance. And so in some sense, people have said, well, if you're going to do hypothesis testing on treatment effects within leaves, shouldn't your objective function somehow anticipate you want to construct a confidence interval? And I'll say, well, actually it does because we're going to penalize small leaves that would have high variance and thus would have uninformative confidence intervals. So we basically, instead of doing like nearest neighbors like this, we're going to have tree-based neighborhoods that basically slice up the covariate space according to where we see heterogeneity in the tree building sample, and then in the estimation sample, we'll come back and estimate treatment effects in that partition. So just to give the sample splitting a little bit more, I don't usually show this, but in our PNAS paper, we do simulations to show the trade-off between the mean squared error. You lose mean squared error when you sample split because you're going to build a less complex model, and you won't get the whole sample available to do things. On the other hand, you're going to get better coverage of confidence intervals. So these rows are just different splitting rules. Causal tree is our favorite one. And we basically show that the mean squared error is worse for the honest, for the sample splitting. But the coverage of the 90% confidence intervals, if you're adaptive and you don't do sample splitting, is very poor. But if I do my sample splitting, my coverage is perfect. And it's sort of by construction perfect. Because it's basically as if God gave you the model, and then, of course, you're going to get the right confidence intervals. So we applied that to search. So I did this experiment on Bing where I took right before the users saw the results for a few million users, I re-ranked their results. I took the thing from position 1 and put it in position 3. And so I showed that as you go from, the treatment group, the first position gets 25% of the clicks. If you put that in the third position, they lose about half their clicks. The 6.9% is what the thing in the third position normally got. This shaded blue is sort of the difference between correlation and causality. If you just use observational data, you would think the treatment effect of first versus third position is to lose this whole area. But if you do an experiment, you realize that this is the treatment effect. It's smaller. The reason the answers are different is because the thing in the first position is a better link. And so when you take that better link and put it at the third position, it performs better than the thing that used to be in the third position. So I ran this experiment, and here, this data set, I've got about 600,000 observations. I threw away, based on covariates, some things so that I wouldn't reveal any confidential information. Then I ran the causal tree to try to see where do you get a big or small treatment effect. If a query looks like an image or a celebrity query, there's basically no treatment effect. If it's rated high as Wikipedia reference, so it's sort of an informational query, it gets a bigger than average treatment effect. You lose 22% of the clicks. This is the rest of the tree. One of the things that's kind of interesting, again, getting back to Larry's point on sample splitting, is that if you take the adapt, even though I have hundreds of thousands of observations and I'm only estimating about 20-odd parameters, that's not enough data to avoid bias. Your confidence intervals do not have the right coverage unless you do sample splitting. My adaptive estimates have a variance of the leaf estimates relative to the mean 2.5 times as big as my honest estimates. So hundreds of thousands of observations and 22 parameters, that's not enough data to avoid the curse of overfitting. So just to keep in mind, that's why I think all empirical people should always sample split if they're using machine learning methods to find the model. Okay, so now we go from trees to random forests. So random forests are going to basically be averaging up a whole bunch of trees. We turn a tree into this T star, these different trees, by bagging or subsampling. And it turns out subsampling is much better theoretically than bagging, so we subsample. They're basically the same in practice, but you just can't do the theory with bootstrapping. And then we're going to select the variable at each step from M out of P randomly drawn features. And so what we're going to do in the forest is we're going to make each tree honest. So each tree is going to use one subsample to create the tree and another sample to estimate it. And the really awesome thing about this is that for a single tree, there's a trade-off in mean squared error for sample splitting. In the random forest, you are already using small subsamples, so there's basically no loss. I was already going to use less than 50% of my data to build the tree, and if you look empirically, that typically gives you the best performance to use, we usually find somewhere between 0.25 and 0.5 of your data to build the trees because you want to have lots of different models. So then, basically for free, I'm just going to take the other half of the data and re-estimate. I'm going to do different subsamples every time, so all my data gets used. And so I'm going to get better performance for free. So I think actually somebody could have noticed this like a long time ago but in the machine learning literature, but I think people kind of came to this only when they started to do the theory and realize it. So under some nice assumptions, we get that for a prediction forest as well as a causal forest, we're going to get, they're Gaussian and centered, so you can get centered confidence intervals. We also have an estimator for the variance of the random forest based on the infinitesimal jackknife. And so basically the way this works is you can go out and look for each tree, we can look at the covariance between whether an observation was used in constructing that tree and the prediction from that tree. And so that's going to tell us about the variance of the tree. And this infinitesimal bootstrap works well. The nice thing about the theory is actually for both the prediction theory as well as the estimator for the confidence intervals, it's all based on the theory of classical U statistics. And it's really lovely theory. And Stefan deserves all the credit for that. He taught it to me, and it was very lovely. Okay. So then just to see how it works, like here's a x1 and x2, here's the true treatment effect shown in colors. Our causal forest gets that really well. It draws the corners a little too sharply. KNN starts to smear things because I've got 4 covariates that don't do anything. And when I try to be close in those 4 dimensions, it makes me a less good match in the other 2. When I go to 20 dimensions, KNN or a kernel is just going to smear everything because there's only 2 important dimensions. There's 18 unimportant dimensions, and so you just average everything towards the mean. While the causal forest isn't harmed at all by that because it figures out that they should be paying attention to these 2 dimensions. So it's basically just the same thing as a kernel or KNN, except for it just ignores the garbage very effectively. And it dominates KNN both in mean squared error and in the coverage of the confidence intervals. So just to apply this, we applied it to the General Social Survey where they randomized 2 questions. Are we spending too much or too little on welfare, or too much or too little on assistance to the poor? And we want to look at the treatment effect of phrasing the question differently. So it turns out if you're rich and conservative, you like to give money to the poor, but you don't like welfare. But if you're liberal, you're happy with welfare or giving money to the poor. So that was the work up to date, and then what we want to do now is take this whole apparatus, which works really well, and now bring it to more complicated models. And so for the last year, people kept emailing me and say, oh, this is really cool, but what if I have fixed effects? What if I have time series? What if I have this? What if I have that? And I said, okay, well, I could spend a lot of time or get an army of students or something to do every one of these extensions, but maybe there's a more general way to do this where we can just put up one software package that will do all of them. And this is also very much in the spirit of what Victor has been doing as well. Like a lot of his stuff, he's been extending to these more complicated models. So the bigger picture, we want to think about solving estimating equations with random forests. And we want to use the parts of random forests that work really well, but in more complicated models. So imagine we have an IID sample, and we have some observables O and a set of auxiliary covariates X. And so basically, X are going to be the things we want to get parameter heterogeneity with respect to. So non-parametric regression, we would just have yi as our outcome. Treatment effect estimation, we would have the yi and the treatment. With instrumental variables, I'd have yi, wi, and zi as my observables. And so our parameter, just as Victor set up as well, we're going to have some parameter of interest, but ours is going to be theta of x, and there's also going to be nuisance parameters nu, which might be the fixed effects in the model or other types of things. And so our goal is going to be to estimate theta of x non-parametrically. The relationship with x will be non-parametric. So just to give some examples, we could do quantile regression. And so in the quantile regression, our parameter would just be the quantile of the distribution of outcomes as a function of x. For IV regression, we can write this in terms of the orthogonality between the instrument and the estimating equation, the outcome equation. So the classical approach to this would be to rely on local solutions, and this has been, again, has a very long history, where you would basically, instead of just taking the normal method of moments, if we want to evaluate things at a particular x, we're going to have some sort of weighting function alpha, and we're going to weight local observations more highly. So that would be a kernel, for example. And so what basically we want to do is replace this alpha with data adaptive rates from random forests that are going to do just as good a job as they do in the prediction context and the treatment effect context at basically ignoring irrelevant covariates and also finding complicated interactions that exist in the data. So what we're going to have, so this is going to potentially be a helpful thing to do, but we actually have a number of challenges. So first of all, my first idea at this, and I even programmed this up, was to build lots of trees and then estimate models within the leaves and then sort of average up your results. That actually has a bunch of problems. One is that if your model is nonlinear, then with a treatment effect, like the average of the treatment effects is the average treatment effect. If you have local average treatment effects, that's like a ratio of two averages, and so the local average treatment effect in a subgroup isn't, if you average all of those up, that's not the same as population, and there's all sorts of other problems, particularly that the estimating equations become very unstable within a leaf, and so you sort of create a lot of noise. Quantile regression, for example, also, you need a big sample. So we're going to, instead of just doing this sort of the way I did in my first paper, which was within each leaf, I'm going to estimate a treatment effect and then sort of average those up. Instead, I'm just going to use the kernel to build the weights. But I want to make sure that when I build those weights, I need to be thinking about my goal. So if my goal is an IV regression, I need to be sensitive to heterogeneity in the first stage and the second stage. So I need when I build the forest, I need to know that I'm building a complicated model at the end. I need to know what that model is to figure out where the relevant heterogeneity is. But at the end, I'm just going to use them as weights. So you can think about building all of these different trees. My splitting rule is going to be customized to my objective. But then if I think about, for a particular x, how do I weight my observations? I'm going to weight them by how often they're in the same leaf. So like these observations up here are getting more weight because they ended up in the same leaf as x more often. Now this idea was used by Meinhausen in 2006 for quantile regression, and there's actually an R package for that. But the problem he didn't solve was the splitting rules. So he actually just built the trees as if you were doing regular regression and then estimated quantiles. And so I'll show you in a minute where that can go wrong. First, I want to talk about some more challenges, and now we're getting kind of more into the machine learning engineering side of things. Like this algorithm actually has to work in practice, and it has to be computable. So a few problems. We don't know what the prediction error is for our parameter, so we have to optimize splitting. We need to think about nuisance parameters, and we need to be computationally efficient. So first of all, we're going to use greedy splits, and we're going to think about our ideal goal is going to be just to find heterogeneity in our parameter rather than heterogeneity in predicted values. So The second piece, a little more novel, although it's really inspired by a very common trick that's used, for example, in gradient boosting. So what we're going to do is we're going to think about, if we want to think about, say we have a parent leaf and we want to split it into children, what CART would do for a regression tree is it would check every possible split, and so you'd basically have to recalculate the mean for every possible split. Now, if I'm doing a big GMM model, that gets really expensive because I would have to go through every covariate and every possible split and re-estimate my GMM model. So that sounds hard. So we're going to skip that and basically say we're just going to take the parameter estimate theta p from the parent, and then we're going to basically take the gradient of our GMM function, and we're going to create these sort of pseudo outcomes and use those in our regression tree. So we're going to basically think about approximating the child's parameter as just taking a Newton step evaluated at the parent's parameter. So we're not going to keep re-estimating the parameter at every step. We're just going to basically be looking at the gradient evaluated at the parent parameters. So once we write this down, we can actually think about how we're going to implement things. We're going to create pseudo outcomes, which are basically this gradient step from the previous slide. And so we can think about these sort of pseudo outcomes as our outcome that we would use for a regression tree. And so we're basically going to try to divide up our leaves according to heterogeneity in the extent to which sort of this observation is different than the average in the parent. So this is going to mean that we only have to solve the estimating equation once for the parent, and it also reduces the risk of hitting a numerically unstable leaf. So also we're going to be searching over lots and lots of possible splits. So if things are numerically unstable, you're going to end up making mistakes because you're searching over so many splits. You're going to find one that's kind of crazy. And from an engineering perspective, what's nice about this algorithm is that I basically going to have like one splitting rule that I can, as long as I know what the moment equations are, I can use the same software over and over again. So I don't have to have an army of RAs to implement every possible variation. Another thing we need to do, and this is really inspired by what Hito and I do in our treatment effects paper. I mentioned that when you anticipate honest estimation, which we do here, you're going to want to think about penalizing leaves that create a lot of variance. And so we found in practice that it's very important to do that. And if you just think about an application to IV, one thing that might happen is you start sort of splitting your data set more and more finely is you might get a leaf where basically you're not identified anymore. Like you might be identified in the whole sample, but you might get a leaf where there's just not a lot of power of your instrument. And so by explicitly computing the variance of your estimator and penalizing high variance estimators, you're going to avoid going into kind of unidentified parts of the parameter space. So we put all that together, and let me just show you some examples. So first, let me show you quantiles. If you take our algorithm, the kind of pseudo outcome you would use for the quantile regression would be an indicator for whether yi is greater than the quantile of the parent. And so that's what, when you take the gradient, that's what you end up with. And so we would split based on heterogeneity in that object. Here are some simulations, and here what we're trying to show is that it makes a difference whether you use, what splitting rule you use. I'll focus on case 2 here. Here x shifts the scale of the outcome, and so it's going to shift the 25th and 75th percent quantiles, but not shift the mean. And so if you use the R package, you don't split because the mean doesn't actually change in x, but you do split using R splitting rule. We have some simulations for IV as well. Let me actually just skip to the application because I'm just about out of time. So we applied this to Angrist and Evans, their family size paper. Outcomes are participation. Treatment is having more than 2 kids. And the instrument is whether the first 2 kids are the same sex. And so we go back to that data set, and then we use our algorithm to look for heterogeneity in the treatment effects. By the way, we also are looking at the perturbed data set you were looking at as well, but so good thing I picked a different one. So here, but we're looking for treatment effect heterogeneity as opposed to just the average effect over all the people. And so for here, like we can see how the effect of having more kids on labor force participation is sort of non-monotonic and non-linear in the father's income, and it also depends on the age of the mother at the first birth. These are a little hard to interpret because the baseline probability of working also varies with all those objects, and so here's one that's sort of normalized by the probability of working, when you still see this kind of hump shape in terms of father's income, that there's sort of the rich people, the mothers aren't working anyways, so it doesn't matter so much, but in the middle range of income, it can matter a lot. So that's my last slide. So he's showing me end. Just to conclude then, kind of the motivation here broadly is that random forests, as Larry very well motivated, work really well in practice. We don't know exactly why. There might have been theory to say they work badly. Actually, they do work a little bit badly theoretically off the shelf, but you can modify them just a little bit using sample splitting. Don't give up very much. Get all your nice theoretical properties. Once you have that, then we can take this very powerful idea not just to treatment effects, but also to more complicated models. But the sample splitting is a really important part of making sure that you're getting unbiased estimates. But beyond that, we're able to kind of use the power and performance of these models very well. Maybe one last caveat, though. I would say we do get nice confidence intervals, but it is if you're doing personalized predictions and you have a lot of covariates and not a lot of observations, it's sort of theoretically impossible to really get perfect confidence intervals. So, we have a theorem, but you should be cautious with the actual literal interpretation of them. If you really want your confidence intervals to be right, it can help to change the question, like look at subpopulations and learn something about a subpopulation where you actually have enough data to get a good confidence interval. Okay.